Okay, continuing on with our review of assumptions related to linear regression. We will follow up now. We just got through looking at generating residuals plots and kind of inspecting them for evidence of any kind of nonlinear trends between the independent and dependent variables, and also looking for evidence of non-constant variance. And really, none of that was present in the data. So we're going to continue on by looking at another assumption related to the residuals in regression, and that is the assumption of normality of the residuals. So in the previous video, I mentioned that basically residuals are prediction errors, and it's the difference between a case's actual observation on y and the fitted value on y. And we talked about this, residuals were assumed to be, essentially randomly distributed within the residuals plot, that they would exhibit, constant variance. Another assumption, though, is that the residuals exhibit normality. And technically speaking, this assumption concerns the conditional distributions for the residuals. So, and what I mean by that is that when you have your predictor variable, again, I'm going to just use a bivariate relationship here between x and y. So if you can kind of imagine, let's say I have a plot of data points that are are dispersed around the prediction line. The idea is that let's say this is x equals 1, x equals 2, x equals 3, x equals 4, and x equals 5. So the distributions we're assuming are of the residuals are normal, and so these distributions, though, these are conditional on the value of x. And so the basic idea is that at each value of x, we have a normal distribution of the residuals. And then, like I said before, we also make the assumption that those distributions have equal variances. But nevertheless, we're mainly focusing on the issue of normality. And we don't really look at the conditional distributions as a follow-up. A lot of times what we end up doing is just sort of pooling all of the residuals and then looking to see if, in general, the residuals are exhibiting a normal distribution. So what we can do in order to accomplish this is that we can use, basically utilize either descriptive techniques or significance tests in order to kind of look to see if we're meeting or violating that assumption. So, really a good starting point is, we can start off by just generating skewness and kurtosis statistics of the residuals. And so, using this command right here, I'm just using summarize and then detail, and then this is the name of the my variable in the data set, which is for unstandardized residuals. So I'm just going to, type that in, and again, using our looking at our data set right here, this is for the unstandardized residuals. And so if I say summarize, this is summarize command, the name of this variable, comma, and then detail, then I get some summary statistics for this particular variable. And so you can see that down here we have skewness and kurtosis statistics. So when you're looking at the issue of normality, just keep in mind there are two dimensions of normality that we have to pay attention to. One pertains to the symmetry of your distribution. And so, when we're dealing, if you think about a normal distribution, we're basically saying that, the proportion of scores, falling on this end equals the proportion on this end. This is where the mean median mode theoretically would line up, and so the distribution is symmetric. If we have a positive skew for that distribution, then it might look a little bit more like this, where essentially we have sort of a longer tail in the upper end of the distribution. and you know, we would have for a negative, so that's a positive skew. Negative skew, we're just basically dealing with a longer tail, kind of in the lower end of the distribution. And these are kind of idealized, but you can see the lack of symmetry relative to what we would expect with a normal distribution. And so the skewness statistic we can look at as being centered at 0, and a positive value would indicate more positive skew in the data, a negative value indicating more negative skew. And really, you know, from a descriptive standpoint, what we're looking for largely are values that would fall between, you know, a -1 and a +1, ideally. You know, there are various rules of thumb. Some researchers have more stringent thresholds than others. You know, this is a fairly liberal threshold for saying that we have a substantial departure from normality on the skewness dimension. Another possibility is to use the -2 to +2 as sort of your thresholds. But at any rate, you can see right here that skewness for the residuals is -0.34. So it's falling, you know, kind of within this range right here. So we would not, from a descriptive standpoint, it's not a substantial problem. Now, kurtosis has to do with the relative peakiness to the tailness of a distribution. And so there's a great article written in 1997 by DiCarlo, and basically you have to think about the relationship between the normal distribution and distributions that exhibit, you know, these different types of kurtosis. So, you know, a platykurtic distribution is one where basically you have kind of thinner tails and it's really more flat. So it's more rectangular in shape. Whereas, you know, a leptokurtic distribution, you have kind of thicker tails and, you know, more peak right here. And so you can see that, you know, essentially the areas falling under the curve are distributed differently relative to a normal distribution. So, at any rate, it's kind of a common misconception that you know, when we're talking about kurtosis, that it's all about how peaked the distribution is. It's actually the relationship of the peakiness to the tailness of the distribution that matters. So if you happen to have a more leptokurtic distribution, you know, if we use this sort of same type of scale, a positive value would indicate greater leptokurtic type of distribution. Negative value would indicate more of a platykurtic distribution. And so the value is positive. And again, there are various rules of thumb for evaluating what constitutes, you know, a substantial departure from normality. I think in textbook that I use, the authors, it was by Lomax and Hasvan, they suggested, you know, similar to the skewness, you know, values that kind of fall in that -1 to +1 or -2 to +2 range for considering the kurtosis as being more substantial. So really kind of using either of those approaches, it looks like there might be some evidence of some departure from normality. This is basically a descriptive approach for evaluating normality. I might also wish to carry out a significance test to evaluate the normality of the residuals. So the way that I can do this is, you know, kind of just looking at the syntax here. You can see I can use this command right here, skTest, and then the name of the variable. So I'm going to say skTest UR for my unstandardized residuals variable, and hit enter. And so this is a significance test really of each dimension in terms of related to normality, as well as the combined information concerning skewness and kurtosis. So we have a probability value associated with skewness, and you know, keep in mind that basically when you're using tests like this, the null hypothesis is that the data are consistent with a normal distribution. The alternative hypothesis is that the data are inconsistent with the assumption, in this case, normality. So in a nutshell, if I set alpha at 0.05, as a conventional threshold. If I get a p-value that is, less than or equal to the 0.05 level, then I would end up rejecting the null and concluding that we have a potential violation of normality, either in terms of the individual dimension related to normality or just the general departure from normality overall. So you can see that in terms of the skewness and kurtosis statistic, those p-values are greater than 0.05, which would be an indication that our data are reasonably normal on those dimensions. And then we have the significance test overall in terms of whether or not the data are departing from normality. And you can see that our p-value is greater than 0.05, and so we would have evidence that the residuals appear to be fairly normally distributed. Keep in mind that, as with any significance test, the larger your sample size, the greater likelihood that you will end up rejecting the null. Basically, as sample size increases, you have a more powerful test. So even a modest departure from normality could still be deemed statistically significant with tests like this. So it's worthwhile to also, kind of look at, the descriptive information, and then also, look at plots of your data. The other thing to note is that, with sample size, it could be that if you have a very low n, then even with a fairly larger departure from normality, you might not reject the null. And so you just have to kind of keep in mind that you need to be looking at both the the significance test results as well as more descriptive information. Another test that you could use is the Shapiro-Wilk test. That's another test for normality. And so if I just type in SWILK and then the name of the variable, then there it is. And so that's yet another significance test to determine if your data are departing substantially from normality. Okay, so then we can also kind of look at normality visually by looking at PP and QQ plots. And so essentially what I can do is I can type in P norm UR, and this is a plot, basically, kind of plotting your data against what would be expected with a normal distribution. And so what we're looking for is that the data points are following reasonably closely to this line. And, in places where the data are departing substantially, then that might be evidence that we would have a departure from normality. So we have sort of, the data are largely consistent. It looks like they're following pretty closely to the line. It's not perfect, but it's not enough to give me a whole lot of pause concerning that issue. Another plot is the QQ plots. So I can just type in Q norm UR for the unstandardized residuals, and there it is again. And so you can see maybe a little bit more deviation down here in terms of the plot, and then some departure from that line right here. So there's maybe a little bit of mixed evidence in terms of the issue of normality, but in large part, I would say it's probably reasonably in the ballpark. It's reasonably consistent with what we would expect with normally distributed residuals. So at any rate, moving on, we can also look at, I mentioned before that we have the assumption of constant variances, and so we've already kind of looked at that issue visually using the residuals plot. Another option is to carry out a significance test, kind of like what we did with normality just a second ago. And so there are actually two tests that we can utilize. There's the Breusch-Pagan and White's test. And the basic idea is that if we reject the null, if we find a test result indicating statistical significance, then we would take that, hopefully in combination with the residual plot information, and determine, if we reject the null, then we would be assuming that our data aren't meeting the constant variance assumption. So at any rate, we'll take this information right here. If I just type in estat het test down here, so I'll just type that in, estat het test. Then I get a significance test. This is the Breusch-Pagan test, and it's testing again the constant variance assumption. So you can see that the p-value that is printed out right here, it's not less than 0.05. So we would end up maintaining the null and inferring that the residuals exhibit constant variance across levels of your fitted values and your predictors. So that's a good thing. And so again, this kind of backs up what we saw previously with respect to the residuals plot. Another possibility is to use this other test. I mean, so you can actually use both of these. And I'm just going to copy and paste in here the IM test. And here you can see we have looking at heteroskedasticity, and we can see if we have statistical significance, and obviously that's not significant either. So really both of our test results are suggesting that the constant variance assumption appears to be met, and they're very much consistent with what we saw with the residuals plot. Another question that we might have is just looking at, if we want to look at just kind of visually inspect or determine if we have any kind of non-normality in terms of the individual variables within the regression model, or any kind of multivariate non-normality. Sometimes we have certain analyses that make assumptions related to multivariate normality, and so particularly if we're working with maximum likelihood estimation, that's one assumption related to that. And so if we wanted to ask for those kinds of that kind of information, we can do that. So let's say I just want to ask for univariate, bivariate, and multivariate normality tests concerning our variables in the model. So I would just type in MV test normality. So that's the basic command. And then I would just include the variables in the model. So I'm going to move subject matter interest, mastery goals over, anxiety over, and achieve over. Those are some examples there. And then comma, and then I can ask for univariate, bivariate as well. And again, you got to make sure that you spell things correctly, or else it's not going to work. So I misspelled normality here. And there we go. So you can see, in terms of the output, some useful information. So we've got, again, the skewness and kurtosis statistics. This is just this was just from a subset of our variables, but you got subject matter interest, mastery. This is for the predictors themselves in the model. So there's skewness and kurtosis statistics for each of those. The joint tests for normality. So all of them appear to be reasonably normal based on these tests. We have tests of bivariate normality between subject matter interest and mastery goals, subject matter interest and anxiety, mastery goals and anxiety, and none of these are significant. So there's evidence, that we're meeting the assumption. Well, our data are following a bivariate normal distribution, and then we also have the test for multivariate normality. So it's just basically looking overall among all those variables, is there a significant departure from multivariate normality? And it's a little closer on that one. It's 0.0596, but so that's a little something to kind of take into account. But again, this is kind of a useful approach if you want to look at multivariate normality related to the variables in your model. And I inadvertently left out the achieve variable. If I want to include that as well, I can certainly do that. And so there it is. So you can see there's achieve, evidence of normality, univariate normality. In terms of bivariate normality, there might be some departure with respect to its relationship to its subject matter interest, but not with anxiety or mastery goals. The multivariate test also it wasn't statistically significant, but it was kind of in the near ballpark, I guess you could say. So, but again, you want to be able to inspect your data in multiple ways, and kind of, if you have departure from normality in terms of the residuals, or problematic behavior of the residuals, non-constant variance, and so forth. These are useful follow-up tests to kind of potentially identify sources of any kind of departures on some of those other assumptions.